Hey y'all, it's your personal math teacher, Mr. Boyden, back at it again. Today we're going to be going a little bit deeper into probability and adding on to some of the things that we learned last time. So let's not delay, let's act now. Supplies are running out, let's do this. The first thing we're going to talk about today is just the concept of a sample space. Sample space is a very simple concept. It's just the set of things that could happen. So let's do an example and let's get right into it. You throw a six-sided die, we're talking dice, right? And we want to know what is the sample space of that. Okay, remember, the sample space is the set of all the possible outcomes for a given situation. And so a lot of times in class when I give this example, people will say the sample space is 6. And I think what they mean is that there are 6 different things that can happen. And that's true, there are 6 different things. The 6 different things are 1, 2, 3, 4, 5, and 6. Those are the 6 things. So this is the sample space. It's the set of all the things. It's not that 6 is it. If you say 6 is your answer, you're saying the only thing that can happen when you throw a die is you get a 6. No. We can get a 1, 2, 3, 4, 5. Or you knew that. I'm sure you already knew that. But if you were thinking that way, just be careful. Okay. Now, the underpinnings of probability are pretty basic. Okay. And it's really this right here. Okay. It's that the probability of something happening. So probability of event A is the number of equally likely ways that A can happen divided by the number of total outcomes in the sample space. So we're going to do an example down here with that same die that had the sample space up above. And here it is. You throw the die. What's the probability of getting a 2 or higher? So what we have to think about is how many different ways could we get a 2 or higher? Well, we could get a 2, a 3, a 4, a 5, or a 6. So there's 5 ways that could happen, and they're all equally likely. Out of 6 different things that could happen, so the probability of getting a 2 or higher is 5 out of 6. Okay? And yeah, we build from there, but that's like the basic idea of what probability is. Okay, so anytime something gets really overwhelming, always go back to that and think, okay, how does it relate to that basic idea? Number of ways something can occur divided by the number of outcomes in the sample space. Next thing we're going to talk about is the idea of complementary events. Now, I mentioned this in the previous video. We were doing the example with HIV and we said something like, 0.3%. 0.3% of people have HIV, which means that, 0.3%, I should write it as a percentage, which means that 99.7% of people are HIV negative, and those two add up to 100%. That's how I got that 99.7 in the previous video. Okay, and that's what a complementary event is. Okay, it's saying the probability of an event happening and not happening. So think of this as the probability of A not happening. That's what a complement is. And so the probability of it happening plus the probability of it not happening is a 1. Okay, I'll give you another simple example. The probability of me getting hit by a bus today plus the probability of me not getting hit by a bus today is 1. It's guaranteed that one of those two things is going to happen. I'm either going to or I'm not. And it's kind of late in the evening and I'm in my house and I don't think I'm going out tonight. So hopefully I don't get hit by a bus in my house. That'd be really weird. All right. Next example. We're going to do another one with complementary events. I guess one thing I didn't say is about the spelling. It's not compliment with an I, like, oh, your hair is looking very nice. It's not that kind of compliment, okay? It's more compliment like complete, like it completes it. That's why it adds up to 1. It's the sum total of everything that can happen, the complete set of outcomes. So it's not like, oh, your hair is so nice. It's more like, you complete me. It's more like that, okay? All right, example. The probability of getting into Stanford, oh man, this is rough, 0.014. What is the probability of not getting into Stanford? Well, it'd be 1 minus 0.014, which is what, 0.986, I think? I'm doing mental math. Hopefully I got that right. I think that's right. Okay, so that's the complementary probability. All right, let's keep going. What about mutually exclusive events? Okay, 2 events are mutually exclusive if they could never happen at the same time. Okay, so we have a little bit of notation over here, and I want to annotate what's going on over here on the right a little bit and give you a chance to write that down. This symbol right here, it is called an intersection, and it represents the word and. Okay, so what does that mean in this context? This is the probability of B and A both happening is 0. That's what we mean by mutually exclusive. They couldn't both happen, so the probability of A and B happening is 0. Okay. Well, you can remember, by the way, that it's an and is this symbol in here. Kind of looks like a letter A if you put a little crossbar on it. Okay, so that's it. It's a total coincidence that it looks like that, but that's one way you could choose to remember. That's how I remembered it when I was learning. Okay. And when events are mutually exclusive, we can use the addition rule to find probabilities. So, for example, oh, new symbol. Possibly new. You probably learned this in an earlier class with me. This symbol is called a union, and it translates as the word or. Okay, so in a way you can remember that it's a union is it looks like a U. Okay, so this is like the probability of A or B happening is you just add the probability of A and the probability of B happening together. Let's do an example of mutually exclusive events. Okay, let's do like the simple classic example. Flip a coin. Event A is getting heads. Event B is getting tails. When you flip the coin, those are mutually exclusive because they couldn't both happen. And let's compute the probability of their union. So the probability of A union B. Remember, A is getting heads. What's the probability of getting heads? That's 1/2. So I'm just pulling that right there. Plus the probability of B getting tails. That's also 1/2. And that equals 1. So that's the probability of flipping a coin and either getting heads or tails. Pretty well guaranteed. Now, someone in class always says, but Mr. Boyden, what if it landed on its edge? Or what if it never came down? What if gravity stopped working? Okay, you got me. You win. Okay, you win. If you were thinking that. You got me. All right. All right. We also need to be able to do probability from two-way tables. My suggestion for this section is that you pause the video right now and read the question and write down the table. All right. So here it is. The two-way table below summarizes data about gender and subject preference for 25 students. So meaning, do they prefer to do math or prefer to do English? And I just have to make a note of, obviously, more people prefer math than English. I mean, as if you didn't already know. Come on. So we're going to we're going to choose a student at random out of these 25, and we're going to let A be the probability of randomly selecting a male, and B is going to be the probability of randomly selecting a student who prefers math. Now, what we're going to do here is we're going to do a whole bunch of questions on this situation. And some of these symbols might be new to you, and that's okay. Some of this you're going to want to pause and try yourself first. Some of this you're going to want to pause and hear me say it twice because it didn't make sense the first time. That's totally fine. Just understand that's part of the game of learning this here, okay? All right, probability of A. That would be the probability of selecting a male at random. So all I'm going to do is look at how many people in the set identified as male, and it looks like there are 10 people who identify as male out of 25, and I can simplify that down to 2/5. So that is the probability of randomly selecting a student, or excuse me, randomly selecting a male. Notice I'm leaving that as a fraction. I don't need it to be a decimal, and it didn't ask for a percentage. It asked for a probability. All right, probability of B. What's B? That would be the probability of randomly selecting a student who prefers math. Who are math prefers? There are 20 math prefers, it looks like. So that's 20 out of 25, which is 4/5. All right. What's the next one? Okay, so what is that symbol? Probability of A intersect B. Remember, that's like the word and. So this is students who identify as male and prefer math. Let's go back to the table. Who are those people? Those males who prefer math males, right here. There's 8 of them out of 25, and so that's what this is. This is 8 out of 25. All right, and I'm just bringing that table down here so I don't have to scroll up and down as much so it doesn't hurt your eyes with me jumping all over the place. Okay, let's keep going. This next one, probability of being male or preferring math. Okay, so what we're going to look at in the table is which of the people in here are male or prefer math. So are these people male or prefer math? Yeah, I'll come back to why in a second because some of you might be going, what the heck? Do these people, are they male or do they prefer math? Yes, they prefer math, so they are male or math. Down here, are these people male or prefer math? Yes, they do because they're male. Are these people male or prefer math? No, they're neither. Okay, so hold up. Let's do the calculation, then we'll talk about these 8 people and why they actually count in this. So 8 plus 2 is 10, and then we got 12 more there. So it looks like that is 22 out of the 25 people. Now, why are these 8 people included? Okay, this gets a little bit confusing for a lot of people. So I want to go back to the word or. Now, the way we use or in common language is not the same way that we use or when we're talking about mathematics or about logic. So I'm going to write out a question here, and I want you to think about what your answer to this would be. It would be, do you want cake or ice cream? Classic birthday party question. You go to a birthday party and say, hey, do you want cake or ice cream? Now, there are only 2 possible right answers to this. And if you say cake, you haven't technically answered the question, because it wasn't asking which one you preferred. I know you. Come on, man. Like, I know that if someone says this to you, they're asking you to pick one of them. But if you look logically at this statement, the question is, do you want? That's what it's asking. And so, if a question is, do you want? No matter what they say next, the only possible right answers are yes or no. Okay. Now, a lot of people will say yes to be funny, like, do you want cake or ice cream? They go, yes, ha 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 ha. Okay, well, actually, those smart alecks are technically right. Now, guys, I'm not saying to go out in the world and do this. In fact, please don't, because people are going to think you're being a smart aleck, and if you say yes to this question, you are being a smart aleck, so don't do that, okay? Be cool. But in terms of logic, actually, yes and no are the only right answers. Now, when you say yes, you're not saying that you like cake. You're not saying you like ice cream. You're saying you like at least one of those 2 things. So if you like both of them, your answer would be yes. I do like cake or ice cream. Okay, so you would still answer yes. And that's why that's included. Because when this says the people who are male or math prefers, these people are male, these people are math prefers. So are they male or math prefers? Yes, they are. Okay, now that might have been, if you've never heard that explanation of the word or before, you may want to hear that again. Because usually in our speech, the word or, if we use it just like casually with friends, we mean the exclusive version of the word or, as in you have to pick one of them. But in math and in logic and in philosophy, the word or, it means that it has to satisfy at least one of the 2 things. It doesn't have to do both. If it was satisfying both, it would be called an and. Okay, like above. All right, let's do the next question. Now, I find that it's easier for a question like part E down here to try to translate that into plain English. So I'm going to do that. So what was A again? A was that male? A was male, okay. So what would this sentence translate into? So not male and prefers math. That's what question E is talking about. It's talking about those people. And so if you can translate that, this question gets way easier. Because then you just go up to the table and you say, okay, in this table, who are the people who are not male, aka female, and who prefer math? So female math preferers are these people. So then you go, oh, well, that's 12 out of the 25 people. Sweet, done. Okay, that's all that is. What about the next one? Whoa. Okay, hold up. I'm going to translate this one too. So this is, now we're looking for people who are male and not male. Now, guys, I get that like gender fluidity is a thing, but in this table, there are no people that we accounted for that are both male and not male. This is 0. These are mutually exclusive events. All right, next one. The next one is saying that you are, or not you, but it says we're talking about people who are male or not male. So hold up. Who are the people in this table? And let me re-enter the table down here. Who are the people in this table who are male or not male? Well, everyone in this table is male or not male, because these 10 are male, these 15 are not, so that's everybody. This probability is 1. No matter who you pick, they're going to be either male or not male. So yes, that's a 1. All right. Now, notice these last 3. They all have something in common. They have that sort of line down the middle. Okay, and so each of these are what's called conditional probability. Now, I introduced this in the previous video, but I didn't go in depth, so I'm going to go way more in depth and hopefully help you to simplify this within your mind. So when we do conditional probability, it's kind of like the first part is a question, and the second part is the denominator. This is asking for, it's saying, what is the probability of selecting a person who, and A was, sorry, I keep checking, guys. I just want to make sure I get it right. The probability, what was it? So A is male. In fact, I'm going to write this down here so I don't forget it again. I keep forgetting. So A is male, B is math preference. All right, so this is asking, what is the probability of selecting a person who is male, given that we are selecting from people who prefer math? Okay, so this vertical bar, this one right here, the one in the middle, it's saying like, hey, warning, the denominator is changing. It's not out of 25 anymore. We're only looking at the people who have that second condition, so people who prefer math. So we're going to look at the table differently now when we go back up here. We're only going to look at that column, or excuse me, the row of math preferers. And now we're going to answer the question by only looking at that row. So let me show you where I'm looking. So I'm only looking here, and that's what I'm going to answer the question from. So now we're going to answer the question, what's the probability of selecting a person who is male? Well, that's 8 out of 20. There's 20 people in that row, and 8 of them are male. So what's that? That's 4 out of 10, or 2 out of 5. Okay. Now, you might wish to try the next question without my help. So it'd be a super cool thing if you wanted to pause the video and try that out. Because it's the same thing just in reverse. And so it's going to have, it potentially is going to have a different answer, but it's the same concept. So you may want to give that a shot. I'm going to start now. So pause if you don't want to have me spoil it for you. This is the probability of selecting a person who, and B was, who prefers math, given that we are only looking at people who identify as male. That's the A part. Okay, that's so you can see what I'm doing. I'm translating each of these into a sentence. So now we're only going to look at the male column, and looking only at that column, we're going to say, okay, who in this column prefers math? That would be the 8 out of 10. 8 out of 10, which would be the same thing as 4 out of 5. Okay, so that's how that one reads. Now, oh boy, we're putting multiple concepts together on this last one. It would be an awesome thing if you wanted to pause and try to translate this one and write out a sentence for what this means on your own, and then get feedback when you hit play. So this is asking the probability of selecting a person who prefers math if we are looking at people who are, let me go to a new line here. If we are looking at people who, now not A, who do not identify as male. Now in this chart, again, that not male just means female. So we're going to look at the column of female, and looking only at female. Now we're going to do math preference. Math preference for female is 12 out of 15. Which we can simplify down to 4 out of 5. Okay, so I want to encourage you, if you ever get stuck on these, I mean, I used to get stuck, and some teachers will like throw formulas on top of formulas at you. I don't think it's useful. Ultimately, you have to know how to read the symbols. And for me, I can do it in my head and then get it off of the chart, but it's so much easier if I write something down. Now, if I'm honest with you, when I'm actually answering questions like this or making an answer key or doing a practice test to work on my own skills, I don't write the full sentence. I write out like just a few words. Okay, so like for example, on the first one, I would say male given math is what I would write down, just to translate it into words that fit the table, and then off I go. Okay, last thing we're going to do today is we're going to talk about Venn diagrams. Now, Venn diagrams is something that I think you probably learned about. I don't know. I'm not sure when you learned about them. I learned about Venn diagrams like in elementary school. And so we would use them as a way to compare and contrast. And so we would have two things like things that fly and animals. Animals, okay? And so then we'd figure out, okay, well, things that fly, you know, like a bird is an animal that flies, and maybe a bee is an animal that flies, and a tiger is an animal that does not fly, and an airplane is a thing that flies, but it's not an animal. And so then we'd say, okay, well, these are things that are, you know, have both characteristics, and then some things have one or the other. And that's totally fine. I don't think I realized until I was a little older that Venn diagrams potentially could be useful for doing math problems, which was pretty exciting because I liked them when I was a kid. And then when I realized they were versatile, I liked them even more. Okay, so let's try to answer a question that I'm claiming a Venn diagram will help us with. So here we go. According to a poll, Pandora and Spotify are the most commonly used apps for streaming music. 68% of people use Pandora, 38% of people use Spotify, and 24% of people use both. What percentage use neither? Okay, and what percentage of Pandora users also use Spotify? All right, let's make the Venn diagram. Now, at this level, we typically put our Venn diagrams in a box so you can tell where they end, because we're going to have numbers outside the bubbles. And I know that sounds trivial, like normally you wouldn't need to know, but in math it's useful to know where the diagram ends, so we put them in a box. So let's make some bubbles. And here's the first one. I'm going to call the first one Pandora. I'm going to call the next one Spotify. And let's start filling this out. So 68% of people use Pandora, so 0.68, and 38% use Spotify, so 0.38, and 24% use both, so 0.24, and then we want to use what percentage use neither. Now, guys, that number for neither is going to go out here somewhere, saying that it's not inside either of the bubbles. So, how are we going to figure that out? Well, the first thing I want to do is I want to notice something about these three numbers. In fact, I'm going to add those up real quick and see what I get, because maybe it has something to do with that. So 0.68 plus 0.24 plus 0.38. And guess what? I got 1.3 or 130%. So we already have accounted for 130% of all people. Yowzers. Okay, that's not good. You can't have more than 100% inside a Venn diagram. So there's a problem. Now, where is that problem? I want you to look just for a minute only at the Pandora bubble. According to this diagram that I've drawn, what am I claiming? What percentage of people am I claiming use Pandora? Because we got a 0.68 in there and a 0.24. So I'm actually claiming that 92% of people use Pandora. That's not right. Whatever I write down in my diagram, the end result, or sort of the punchline of that, needs to say that 68% of people use Pandora. Now, I can't change that number. There's nothing I can do about that. But I can change this one. So I'm going to subtract 0.24 off of it. Oops, except I wrote like a 2 and a 4 in one symbol. That's kind of weird. So I'm going to subtract 0.24, and I get 0.44. So let me just cross that out. Now check it out. If I look inside the Pandora bubble, now those two numbers do add up to 68%. Let's do the exact same thing by looking at the Spotify bubble. It says that the Spotify bubble should have 38 in it, but it doesn't. It's got a lot more than that. So I need to subtract 0.24, and I get 0.14. Now, if you double check, if I add 0.14 and 0.24 together, they add up to the 38 that they're supposed to. So I'm going to now redo that calculation now that I fixed my Venn diagram. Now, guys, by the way, I didn't do anything wrong in this diagram. I just wasn't done yet. Okay, so normally I'll write down all those numbers knowing they're going to be wrong, because doing that helps me to realize what I need to subtract. Okay, so now I'm going to double check. According to this diagram, we have 0.44 and 0.24 and 0.14. That's a total of, we have 82% accounted for. So what does that tell us? 82% of people use Pandora or Spotify, yes, or both, but that's included when I say Pandora or Spotify, which means that 18% use neither. So 18% is the answer. And so that Venn diagram makes it relatively easy to, because otherwise the accounting with this stuff gets kind of hard. The Venn diagram makes it pretty easy. Now, let's do part B. What percentage of Pandora users also use Spotify? Ooh, did you catch it? This is a conditional probability. The question is about Pandora users. It asked about Pandora users. And of the Pandora users, so this is the condition. And it's saying of those people, what percentage of them use Spotify? So what this is kind of saying is like, hey, to answer this question, only look at the Pandora bubble. Okay, so I'm looking at the Pandora bubble. How many of those use Spotify? 0.24 of them use Spotify out of all of, now remember the condition is the denominator. We said that earlier. Okay, so the denominator is these two added together, or if you prefer, this 68% up here, out of 0.68. So let's type that in, 0.24 divided by 0.68. And that is, they asked for a percentage. I'm going to round to the nearest whole. That's 35%. Okay, so conditional probability can come in different ways. Okay, it can be like that bar, so probability A given B, or it can be couched in language. So what percentage of Pandora users? So this is who they're asking about, and then within that, they're asking what percentage of them fall into this other category as well, into that intersection in this case. That is the intersection in there. Okay, so guys, I think that's enough for today. Thanks for making it to the end of the video. And I hope you'll come back again so that I can see you next time.